Okay, let's get over to the multiplication part. So there are two types of multiplication that we can carry out between two vector quantities, right? The one is your dot product and the another one is cross product. So dot product between two vectors will give you a scalar output, whereas the cross product will give you a vector output. And you already know about it, I guess. Whenever we are trying to perform a dot product between two vectors seemingly A and B, and whenever we are carrying out a dot product between two vectors given by A and B, the formula that we will be following is AB cos theta. So A means the magnitude of A, B means the magnitude of B, and theta means the inclination angle between those two. Say, for example, this is A vector and this is B vector, right? So theta is the angle of inclination between them. We also have a comprehensive formula that we are familiar with to perform dot product, that is given by ax into bx plus ay into by plus cz into bz. Basically, we're just multiplying the like components of a and b and just adding them together, and all of them are scalar quantities, so the sum will also give you a scalar, right? And there are some other things that you can recap if you want, like if you dot one vector with itself, you will get a into cos 0, right? A vector is inclined by 0 degree with itself, so we will get a square. This is not when we perform the dot operation between the axis unit vectors like I and j, for example. I dot j will give you a 1 into cos 90, because x-axis and y-axis are inclined at an angle of 90 degree between themselves. So this result will give you a 0 because cos 90 is 0. And this is the exact result you will get when you perform a dot operation between j and k, and also I and k, or k and I. If you just move around and change the order they're carried out, they will give you the same result, because the end result is always a scalar. But if you were to dot a unit vector with itself, it will give you just 1, because 1 into cos 90, right? This is what we have just said earlier, a square, that means the magnitude square, so 1 square. And this is what we'll get if you dot j with j and k with k. All right. So let me explain a little what this means. Whenever you are performing a dot operation between two vectors, it denotes the component of one vector along the other. For example, if you take the projection of B vector over A, I mean, whenever you are projecting or taking the shadow of B over A, you will get this magnitude, right? This amount over here. So this little component is the component of B along A. Component of B along the direction of A. So whenever you are performing dot operation between two vectors like A and B, it will give you the component of B vector along the direction of A. Or conversely, it will give you the component of or projection of A along the direction of B. Okay, because the sequence or order of dot operation doesn't affect the result, so it will mean the projection of B along the direction of A, or the projection of A along the direction of B. So keep that in mind next time. Now if we get to the other one, the cross product, it will give you a vector output, and the formula goes like a b sine theta and a unit vector. So whenever you are performing a cross product between two vectors, namely a and b, the value or magnitude of the resulting vector will be AB sine theta. Again, theta is the inclination angle between them. But the result will be a vector quantity, the direction of which is perpendicular to both of the component vectors. Right? So this vector over here, uh, since this is a 2D picture I'm drawing, you cannot really see it as a 90-degree angle, but in practice, just think it as A and B is making a plane, and this line over here is perpendicular over this plane. So this is the direction of the result of your cross product. So a cross product gives you a vector that has AB sine theta as its magnitude, and the direction of which is perpendicular to both A and B. All right, and this eta is the unit vector along that direction. So if you take an unit vector along this direction, this will be eta. And also we'll have another comprehensive formula to calculate it, and this is given by, sorry, and basically you know how to expand a determinant, right? If we take I, then we'll have to multiply ay bz, and we have to subtract az by from it. Then we will go to the j component over here, and we'll multiply az bx and then subtract bzax, right? And if we are to get the k component, we will simply multiply ax by, these two, and subtract ay bx. So this is the formula to get the resultant vector directly. So you'll have to keep in mind this formula and how to break them down. Okay, so let me explain how how can you get the perpendicular vector over here. So imagine your right hand is placed along a direction with the fingers, all of the fingers pointing to the a direction, your right hand. And then you start moving your right hand, you start uh, folding your the fingers of your right hand towards the direction of B, like this. Okay, in this process your thumb, the thumb of the right hand, will point to the direction of the eta vector. All right, so that's how you'll get the direction of the cross product vector. All right. So we have to notice a few things over here. If we were to do the same thing but in a different order, let's say if we were to carry out B cross A, then we would have to first keep all our fingers pointing, fingers of the right hand pointing towards B direction. Then we would have to fold all our fingers towards A direction. Please do that as I say, and see where your right hand thumb points at, and you will find that your right hand, the thumb of your right hand, will point to the downward direction, right? So this time the eta is not the same as before. So the direction of B cross A is 180 degrees apart from the direction of A cross B. That means these two are not commutative. So you cannot write A cross B equals to B cross A. This is not how it works. What you can write, however, is A cross B is equals to minus B cross A. It's because the value remains the same, the magnitude remains the same, but the direction just alters. So the minus will take care of that. But in the case of dot products, we got those were commutative because these simply gave us the scalar value. So the order of the product, order of the multiplication didn't matter. And now let's say you're performing a cross product between I and j. So if you try to carry out I cross j, what you'll get is k. Why is that? It's because I and j and k, they all are unit vectors, so their magnitudes are individually one. And if you just take your right hand and move the fingers from I to J as shown here in this picture, your thumb will direct at the direction of K, right? So whenever you were crossing between I and J, you will get K. If you cross J and K, however, you will get I, and if you cross K and I, you will get J. So there is a way to keep that keep a track of it. So the way is just write I down, give an arrow over here, write J, another arrow, write K over here, another arrow which finishes at I. Whenever you will cross I and J, you will get the result as K. Whenever you will cross J and K, you will get I, and whenever you will cross K and I, you will get J. But what if you will just alter the order? It's pretty simple. Whenever you are crossing Ji, whenever you are performing J cross I, it should be minus I cross J. So it should be minus K. So whenever you were breaking the direction of this arrow, you will get minus the third quantity. All right. So this is one way to keep these things in mind. So that's pretty much the basics of vector quantities that you will find helpful in the lectures to come, and we will meet you in the second part of the lecture where we will discuss about various coordinate systems. That's all from now, and thank you.